Hi, my name is Tilley, and my study was essentially validating UAV-based crop architecture traits using non-destructive ground truth data. So to start off, in plant breeding, phenotyping is a very important but very labor-intensive task. Breeders and geneticists use it to understand the interactions between genetic and environmental factors, but you need phenotyping to sort of improve, crop growth models and being able to predict traits such as yields. Unoccupied aerial vehicles or UAVs are a very popular phenotyping tool because of their desirable input to output ratio. But you also need ground truth data to make sure that these values that you're getting are correct. So even here, you can see total cost in dollars, both manual and UAV are in the $20,000 range, which is pretty similar. Our traits of interest were plant height and LAI. These are very desirable traits to get. They're very manually difficult to get, but also they have a high association with yield. So you want to get those traits. For choosing our representative plots, we use hybrids from the Genomes to Fields initiative. This initiative essentially uses mass data collection to improve phenotype predictions, but you're limited by models used before in historical conditions and what phenotyping has been done in the past. So here you can see this is our field, and a UAV can capture this whole thing, right? All 1,000 plots, but you can't do that manually. Realistically, to measure all 1,000 plots, it would take 39 hours manually and 60 minutes with UAV. So we ran a PCA on anthesis date and on plant heights, and that way we're able to choose pedigrees with large variance and only do 30 hybrids with 4 reps. And here's our workflow. And for our ground truthing, our height was measured with a meter stick, and we did 12 random plants per plot. And for LAI, that was taken from our plant canopy analyzer by Lightcore Environmental, which basically uses a fisheye lens to find light interception between light, canopy, above canopy, and below canopy. And so here is our sort of data, temporal data. For UAV data extraction, we used a tricopter with multispectral camera. Our orthos were generated, so these are just our images stitched together. For height, we also use a digital surface model, which basically has elevation information, and we're able to get our height map, which is our bare ground field, subtracted with our just plant height from a certain date. And then you can see temporal plots of the height difference. For LAI, it's something similar, but we ran NDVI, or normalized difference vegetation index, and then you're able to get temporal plots and the difference between that. So our preliminary data is pretty promising. You can see this is what we saw in the field essentially, and you can see a difference in height and NDVI, and they're pretty useful. I mean, the UAV is pretty useful in terms of cost and time. So moving forward, we would need to run transformations on our regressions. But if we're able to find an R squared of a certain value, where we will be able to use PHT and LAI into different UAV images and just broaden our scope of trait extraction for G2F specifically. Thank you.
So for the light measurements, you're not using the UAV for those as well?
So yeah, this measurement, this is just a different way to try to get LAI.
Okay.
This is its own sort of tool. You can kind of see it here.
Mm-hmm. So how does the drone accurately predict under canopy light measurements? Do you know?
So this basically for LAI, this is just using the light interception from the canopy to compute it in a different way. We don't need to see the under canopy for our NCVI. Okay. So we're just finding the same value, just a completely different way. But we're hoping it ends up being the same.
Great, thank you so much.